I want to talk about one other purpose of a capacitor. And that one other purpose of a capacitor is that it tries to keep voltage constant. Now, it only has a limited amount of charge in it, right? Its charge is Q equals C times V. The way that it tries to keep the voltage constant is to deliver a current, and it will deliver that current until it runs out of charge. Here's an example. The reason, by the way, that we say this is true is it comes from the constitutive relationship for that capacitor right here. I equals C dV dt. So if your voltage is constant, its derivative will be what, Stone? For constant voltage.
Can you repeat the question?
Sure. I'm trying to develop why a capacitor works to keep a voltage constant in a circuit. And it will deliver whatever current's necessary to try to keep that voltage constant. Eventually it will discharge. It only has this much charge in it that it can deliver, but it's going to try to keep the voltage constant in a circuit. Stone, my question to you is, if you've got a circuit that has a constant voltage already, the capacitor should be happy. What's the derivative of the voltage in a constant voltage circuit?
Should be 0.
Right. And so if it's constant, if you're in a constant voltage circuit, the derivative of the voltage will be 0. No current then will flow in the capacitor and everything's happy. But if there is a voltage difference, then a current will be produced by that capacitor that will tend to try to make that voltage less big. And so this is the math behind it, the intuition. Here's this charged capacitor. It's charged up to, say, I don't know, maybe 4 volts. And it really wants to keep that 4 volts there. If all of a sudden there's a tendency for this voltage to change suddenly, maybe it wants to go to -3 volts, this diaphragm will release a large amount of current in this direction that will tend to want to keep that voltage similar, close to 4 volts. Here's how it's actually used in a circuit you may have seen in your own cars. Let's say that there's a cadet and he's got a car. And he's got this big, gigantic stereo system connected to his 12-volt battery. That stereo system goes to a bunch of speakers, including this massive bass woofer. And the battery, this is true of most batteries, it's 12 volts and it can supply a maximum of 500 amps. That's a lot of current. If it's asked to supply over that, the battery voltage will dip. Now, what's a song with a lot of bass?
Old Town Road, sir.
Old Town Road, big bass, thump. And every time that big bass thump happens, it's short. It's maybe only 10 milliseconds, but during that it draws about 1,000 amps. And that's actually a very reasonable thing. If you've got your stereo turned up, the woofers draw an awful lot because your bass requires a lot of air movement. So what happens is that the 12-volt source, the battery, can't supply it. The voltage drops, and the cadet is unhappy. So we're going to fix this with the use of a capacitor. And we're going to put that capacitor in right here. And many of you have seen in high-end car stereo systems, say a 5 farad capacitor. They look like large set of cylinders, large cylinders. It's placed near the battery. And so what happens now? Let me give you the intuition before the math. The intuition is that you've got this 12-volt source pump. And by the way, what makes it 12 volts is that it has a Thevenin equivalent that's got a little bit of resistance to it. Not much resistance, but it's going to be about 12 volts divided by 500 amps. So it really can't supply anything much more than 500 amps without seeing a big voltage drop. Notice the resistance isn't much. 500 amps is a lot, but it will not supply anything. It will not supply an infinite amount of current because of this. And now you've put in this big, gigantic 5 farad capacitor right in here. And it's charged up to the 12 volts that you'd expect. And then it's going, and then lots of current is going in and out of this to your stereo. Now, what happens is that when the stereo asks for 1 kiloamp, the 12 volt source can't supply it because this little restriction will limit it. But this huge capacitor is charged up to 12 volts, and it can definitely, easily supply it for that short period of 10 milliseconds. And then once that base thump is over, then this capacitor can recharge through here, and it can repeat. So here's the math. The math is, you know, that total amount of charge, how much charge is stored in this capacitor, is equal to it's always equal to the integral of current. And in our particular case, if we've got 1000 amps in here for 10 milliseconds up here, that will simplify to 1000 amps times 10 milliseconds, which will be, what will that be? 10, how many coulombs is that? 10 coulombs. How much charge does a capacitor hold? It's C times V. So this 5 farad capacitor, 5 farads is huge. Most of the capacitors we use are millifarads or microfarads, times 12 volts is equal to 60 coulombs that it can store. So every base thump only peels off about 1/6 of the charge that this capacitor is holding. It can provide that easily, and your system stays pretty darn close to a full 12 volts and everything works. Now, for you overachievers who aren't content with that hand-waving explanation, but want to know exactly how much voltage that system, that capacitor will drop in that 10 milliseconds, here's how to figure it out. We know that delta V, the change in voltage across a capacitor between two times, between say time 0 and time 1, is equal to 1 over C times the current that ran through that capacitor integrated up, divided by the capacitance. So if we want to find out how much the capacitor's voltage will drop in that 10 millisecond beat, you can say, well, it's 1/5 of a farad. We're going to integrate that between 0 and 10 milliseconds. And if the battery is providing 500 amps, then the capacitor only needs to supply the remaining 500 amps. So this is a constant. It comes out, and 500 over 5 is 100 times the integral of d tau. From tau goes from 0 to 10 millis. So that's just tau evaluated from tau being 0 to 10 millis. So that would be 10 times 100, which is 1,000 millis minus 0. And 1,000 millis is just a fancy way of saying 1 volt. So there it is. In a 10 millisecond delivery of 500 amps, that capacitor is only going to drop in value by 1 volt. It'll go down from 12 volts to 11 volts, and then the battery will charge it up during the remaining 90% of its time before the next beat.